Section 6.5, properties of logarithms. Our objective for this lesson is to use the properties of logarithms to evaluate logarithms, use the properties of logarithms to expand or condense logarithmic expressions, and then use the change of base formula to evaluate logarithms. Okay, so we're going to be learning, now that we know what a log is and how a log is related to an exponent, we can now start doing some properties of logs. Okay, so first, before we get into our properties of logs, we're going to look at them in relationship to the properties of exponents. So if I have a log base b of m, we know this is equal to some exponent x. So I know if I was going to rewrite this, it would b to the x equals m. Okay, and here log base b of n equals y. So we'd have b to the y equals n. Okay, so if I was going to multiply these two bases, b to the x times b to the y, okay, what we end up doing is we end up taking my exponents and adding them. It ends up being b to the x plus y. That was a property of exponents. We actually add the exponents when we're multiplying with the same base. Okay, so that leads us into our first property of logs, the product property. If I have log base b of m, this is times, there's a little times in there, m times n. So I'm taking the log of this whole piece. I can actually split this into two separate logs. It becomes two separate logs. So if I have the log of a product, I can split it into an addition, and it really comes from this idea. Log of, here I have this product, we add the exponents. So here what we're doing is we're adding the exponents. Since a log equals an exponent, we're adding those exponents. So if I have log base b of m times n, it's the same as taking log base b of m and adding log base b of n. Okay. Okay, we know when we're dividing exponents, b to the x divided by b to the y, we take this x and subtract the y. This would be equal to b to the x minus y. So that leads us into our quotient property of logs. If I have log base b of, again, this whole thing's in the log, m divided by n, it's the same as log base b of m minus log base b of n. So we can actually take the one log, split it up into two separate logs with a subtraction in between. Okay. Okay. Now we have the the power property. Okay, and this comes from this b to the x times the y. Okay, so what I end up doing here is if I have an exponent here and I take it to another exponent, we multiply the x times the y, b to the x times the y. That's what happens here. I have an exponent, because this guy here is really an exponent to another exponent. So then I just take this n and multiply it times the log. So really this n comes out front here, and we multiply it as n times log base b of m. Okay, so if I have an exponent inside of a log, so this is inside this log, if I have an exponent inside the log, our rule is it comes out front and is multiplied by the log. Okay. All right, so one way in which this was used long time ago, back before they had these, if they wanted to figure out logs of weird numbers, they had a table of logs. Okay, they had basically a table that said log that was base 2, and it told you what log base 2 of 3 was, log base 2 of 4 was, log base 2 of 5 was, so forth and so on. And from that table, you would use these properties to approximate all the other logs. So that's what we're going to do here. They tell us log base 2 of 3 is approximately equal to 1.585. Log base 2 of 7 is approximately 2.807. So to evaluate log base 2 of 3/7, so this 3/7 is inside that log, I can use the quotient property, log base 2, 3/7. So I take the log of each piece and subtract it. So this would be the same as log base 2 of 3 minus log base 2 of 7. So now it's 2 logs that we subtract. But I know log base 2 of 3 is approximately 1.585 minus log base 2 of 7 is approximately 2.807. So log base 2 of 3/7 would be approximately 1.585 minus 2.807, approximately negative 1 point, so approximately negative 1.222. Okay, but this one was already broken up for us. It was a 3 divided by 7. Sometimes you have to break it up yourself. Here we have log base 2 of 21, but the only log we know about is 3s and 7s. Well, lucky for us, 3 times 7 is 21. So I'm going to rewrite this as the log base 2 of 3 times 7. So we now have log little base 2 of 3 times 7. Okay. So now I can use my product property, because log base b of m times n is take the log of each piece and add them. So this would be log base 2 of 3 plus log base 2 of 7. Well, log base 2 of 3 we know is 1.585 approximately. Log base 2 of 7 is 2.807. So if I take 1.585 plus 2.807, we get approximately 4.392. Okay, all right, next one. Log base 2 of 49. Well, I don't think 3 goes into 49, but 49 is the same as 7 to the second. So this is the same as log base 2 of 7 to the second. And the reason I needed to go to 7 is because I'm trying to get it to either log base 2 of 7 or log base 2 of 3. Okay, log base 2 of 7 to the second. Well, I can use now my power property. That exponent's now going to come out front, so it would be 2 times log base 2 of 7. So we know log base 2 of 7 is 2.807, so take 2 times 2.807. 2 times 2.807, we get approximately 5.614. Okay. All right, another useful useful way of using these properties of logs is to expand or condense logs. And the reason we do these, you'll see the purpose here in the next section or two when we start solving logs. Okay, so we're going to go ahead and we're going to take this and we're going to expand this. What I mean is I want to write it as a bunch of separate logs. Right now, this is a log base e. Remember, if you don't remember, natural log of x is the same as log base e of x. It's just a shortcut way of writing base e, the natural log. Okay, and we want to split it up. Word of caution, okay, on these expanding, don't do it all at once. Don't do it all at once. Meaning one step at a time. This is a multiple step problem. Okay, but I told you guys that about transformations and you guys still try to do all the transformations at once. So please don't do it all at once. You will make a mistake if you do it all at once. So do one thing at a time. Okay, so the first thing I'm going to notice is I have this division. We have the top, we have the bottom. So I'm going to go ahead and use my division rule, quotient property of a division, and I'm going to split it up into a subtract. So this would be the natural log of 5x to the 7th minus the natural log of y. So the first thing I did is get rid of the division. Okay, now I need to work with this guy. Okay, and so you undo stuff a lot like you undo when solving an equation. I can't do this exponent yet because it's multiplied by a 5 right now. So I'm going to use the multiply. I have 5 times x to the 7th. So I'm going to split this guy up using my product property. So I have 5 times x to the 7th. So I'm going to divide this up into the natural log of 5 plus the natural log of x to the 7th. And then we still have that natural log of y in the back. Okay, so now I have it divided up into 3 logs, but now we can take care of this exponent. We have that exponent. Remember, that exponent's going to come out front, but it's only going to come out front of this guy because that's the only thing the exponent's on. So we'll have the natural log of 5 plus, now simplifying that guy up, the 7's going to come out front here. 7, the natural log of x, minus the natural log of y. So we have the natural log of 5 plus 7, the natural log of x, minus the natural log of y. So I now have it expanded as far as it will go. It's the log of just one thing, the product or sum of logs of just one thing. Again, don't try to go from here to here all in one step. You will make mistakes when doing that. Please do not do that. Okay. All right. Another way of using logs, is we use them, instead of expanding, we can use it to condense. Again, we only do kind of piece by piece. Okay, well, there's nothing I can really do with that. It's just the log of 9. Again, base 10. Again, if they just have log of x, that's assumed it's base 10 of x, which is our common log. Okay, our common log there is base 10. Remember that from the last section? So here we have log of 9, but this one, this is 3 times log of 2. Well, this 3, I can bring it back and make it an exponent. So this would be the log of 2 to the 3rd minus log of 3. Okay. So now I can simplify that 2 to the 3rd. So we'll have the log of 9 plus the log of 2 to the 3rd is 8 minus the log of 3, and then we'll just go left to right. So here these two are an add. So if I'm adding 2 separate logs, I can put them together as a multiply. So this would become 1 log of 9 times 8 minus log of 3. And then from here to here, it's a subtraction, so it's going to be to divide. So I can put it together and write it as 1 log, and it would be the 9, that's not 9.8, 9 times 8 divided by 3. So now we can simplify this. Log of 9 times 8, 72 divided by 3 is 24. So the log of 24. Okay, so this here can be written as just the log of 24. Again, don't try to go just from here to here in one step. Okay. Right. Last but not least, we have our change of base formula. What this allows us to do is it allows us to change the base of any log to whatever base we want. So here we have a log base c of a. This is equal to log base b of a, log base b of c. And I want to kind of connect us where these pieces come from. Here's my a. See where my a is right there? And then here's my original base, base c. And if you notice, this b is a completely new number, and it can be whatever base you want. Okay? Our calculator really only handles 2 kinds of bases. Base 10, log, base e, ln. So what this allows us to do is change any base into base 10 or base e, so we can do it in our calculator. So if I want to evaluate log base 3 of 10 using common log, our common log is base 10. Okay? So what I can do is I can rewrite log base 3 of 8 as, if you notice my a, there's my 8, so that's going to be up here. So log, we're going to go base 10, common log, of the a, which is my 8, divided by log base 10 of the 3. And how I remember this is the base goes in the bottom. The base goes in the bottom. I know we like to call it more the denominator, but it helps me remember with the b's. The base goes in the bottom. So my original base is what goes in the bottom. So I have log base 10 of 8 all divided by log base 10 of 3. So now this is base 10. So I can now evaluate this in your calculator. Oh, sorry, I bumped it again. Okay. So to evaluate this in my calculator, I need to type in log base 10 of 8. So log button of 8, close parentheses. Okay, so there's the log of 8. And I want to take that and divide it by the log of 3, close parentheses. So this is taking the log of 8, dividing it by the log of 3. So again, this is splitting this one log up into 2 logs of whatever base you want. So here we picked base 10 because our calculator can do base 10. Okay, and so we get approximately 1.8927, approximately 1.89, we go 3 decimal places, 1.893, okay? Okay, we wrote this base 10 because our calculator can do base 10, but we could have done it whatever base we wanted. We could have done log base 4 of 8 divided by log base 4 of 3. Again, remember the 8 comes from what you're taking the log of, the 3 is your base. Okay, we also could have done natural log. The natural log of 8 divided by the natural log of 3. We can do that one in our calculator, the natural log of 8, close parentheses, divided by the natural log of 3, and guess what happens? We get the exact same number. It doesn't matter what base you go to. Hence why this is called the change of base formula. It allows you to change a log into any base you want. Okay, so this next one, evaluate log base 6 of 24 using natural logs. And again, a natural log is base E. Okay, so log base 6 of 24 is going to be equal to two natural logs. The natural log divided by natural log, and it's going to be the natural log of 24 divided by the natural log of 6. Be careful, you can't just divide those, because this is the natural log of 6. A very common error. We're going to do a common error over here. Is taking something like this and writing it as the natural log of 24 divided by 6. I'm sorry, I couldn't see, which is the natural log of 4. That does not work. Common error. Caution. Don't do this. Okay? It doesn't work. The natural log of 4 is not the same as the natural log of 24 divided by the natural log of 6. I'll show you. The natural log of 24 divided by the natural log of 6 is equal to 1.777, 1.7737 approximately. The natural log of 4 is 1.38, not the same thing, okay? So don't do that, okay? So we would have to take the natural log of 24, because in order of operations, you do the top, then you do the bottom, then you divide. So the natural log of 24, again, divided by the natural log of 6, ends up giving me 1.774, approximately. Again, we're rounding. Whenever you're rounding, you need to make sure you use approximately sign to let your reader know that it is not the exact answer, we're approximating. So now we can actually use this change of base to find the approximate log of pretty much any number we want with any base we want. Okay. All right, so that's it for 6.5. Go ahead and write the practice down here at the bottom, and good luck.